All right, so today we're going to talk about functions and coding to scale. So functions are another one of these pieces of the puzzle that help us build efficient, scalable programs that are laid out in such a way that you can actually understand what the heck is going on. Now, we all played with functions in the lab. We drew mountains, we drew trees, we drew a sun, we drew a sky. But that was just introducing you to the concept. There's a lot to functions. And functions are an important part of thinking and breaking down problems. They're ways of isolating little bits of functionality. We even have that built into the terms, like functionality is something you can put into a function and have it work on its own in its own little box and then use it when you need to, like circle or rect or triangle. This helps us scale up our programs in ways that are more debuggable, more playable, more flexible, just like we had talked about in the lab. All right, so the whole goal here, and you'll see this when in our next section for class as well, objects and arrays, that encapsulation turns out to be quite important. So encapsulation helps us to deinterlace or to break the dependencies between one part of code and another part of code. And at the scale you've been working at so far, you may not see the need for it, but as your programs grow and get larger, having each subportion of your programs work independently and can be debugged independently and used in other projects independently is quite a powerful thing. So we used to have every game used to be made with its own game engine. Like it was just part and parcel of making a game was making the physics and the graphics and the sound backend for the game to operate. But now we're in this world where we've developed game engines, right? And then you build a game with a game engine, and a game engine brings capabilities like physics, like sound, like the ability to put in assets, like game objects. All those are part of the game engine. They're encapsulated within the game engine for you to use. You don't have to know how each individual thing is programmed, but you have to know how to use it. So this encapsulation of competencies, of capabilities, of data is very handy for us. So functions, they create what we've been calling up to this point a command. Rect, angle mode, create canvas. All those we've been calling it commands or directives that we give to P5 for it to do something for us. Well, someone had to program those or they wouldn't exist, right? There's no magic box that these things pop out of and just work. Someone had to engineer these things, had to make how to draw a rectangle for you to use the rect call. So we're peeling back the layers on how they did this and probably why they did this as well. So we can create our own commands. Because this is P5.js and it has a history of processing, and that was in Java, and Java functions that were associated with classes, which was the only way you could really do them in Java for a large part, was the predominant way you used them. Those were called methods. So sometimes you'll see methods peppered around. We're going to use methods and functions for this class interchangeably. Just give a heads up there. This won't be something that's on the midterm. Just for your own information in case I slip up and say the wrong thing. So draw, setup, rect, fill, all examples of commands that we call, of functions that have been made that we are now using in our programs. Now, modularity, divide and conquer, right? You can make that some really good sense with like ModSynth tunes, or with ModSynth, where you take in a bunch of like synthesizer elements and plug them together to make an interesting track. Well, these little bits of modularity are their own like little reusable chunks. And we're going to do the same thing here with functions. This allows us to look at a problem and divide and conquer. Not to be too militaristic about it, but we want to break down our problems into smaller pieces that are more manageable so that we can then think about solutions to problems and build them up incrementally. We don't have to figure out the entire solution to all of the problem at once. We don't have to big brain this. We can break it down into more manageable pieces and build incrementally. That way, our code is easier to maintain and debug. So if you see a problem and like you get an error in somewhere in your code, and that error is shown at the console at the bottom of Open Processing, it usually has a line number to where the error happened. And that's great because if your line number points to something that's in a function, there's a lot less to understand there. The functions are generally smaller than when you smush all of your code together and all in the draw statement. So functions can replace many lines of code, like we saw with the tree example. We really turned 12 lines of code into 3 calls to our draw tree function, and then like the 8ish lines of code below it. And the more you draw trees, the more you'll get that payoff. The more you will be able to reuse that bit of code, that bit of functionality that you've already created. So write once and use often is sort of the motto we use here. When you're making functions, it's good to think about them as something you can use over and over again. Otherwise, you're just like shuffling code around, which has its own value. But it's not as strong as having something you can reuse multiple times. They allow us to make new commands. So when you're making your own larger programs, when you're working basically for this class on your project, your final project, there's going to be little bits of code you want all the time. Let's say you have like this particle effect when a button is pressed, and you have a bunch of buttons you need to press. Well, you can write that particle effect code once, and then use it every time a button is touched. Right? Instead of copy and pasting a bunch of times, you can reuse it. So that gave you a new command that you didn't have before. And you could also share functions with others in class. You write an interesting one you think everybody would find helpful, put it in Discord. They can use it too. All right. So back to this. Oh, that auto caps in Microsoft products is quite annoying. Okay, there we go. So the general form of functions or a method. We covered this pretty well in lab, but just to reintroduce it to you, it is composed of 4 major pieces. First is the keyword function. When JavaScript encounters the keyword function, it's like, okay, I know the stuff that's coming next is in the form of declaring a function. And the first thing it looks for after the function keyword is the name of the function, which we talked about uses the same variable name restrictions that variables do. So can't start with a number, can't consist entirely of a pre-existing keyword. So you can't have a function called function. And it can have underscores in it and numbers in it after the first letter. And we typically write these in camel case. So lowercase first letter of the first word that composes the function, and other words are then smushed together and capitalized. The initial letter in each word is capitalized in each subsequent word. And then we have our arguments. And we'll look at a lot of these today in class, but this is really the data that your function needs to operate. It's the input. Just like you have f of x equals y. Well, you can see x is like sort of like the input that comes in, right? It's the arguments, the parameters that you pass around that a function uses to do its work. So here we have a list of arguments. With JavaScript, it's quite easy because it's just a set of variable names separated by commas. And then when you call a function, the values that are comma separated when you call the function are simply placed in order in each variable name that is in your argument list. And that argument list, like always, like we've done a bunch of times, is inside of a left paren and right paren, a parenthesis pair. Then the last thing that a function is, and just sort of like the heart of the function, the beating heart of the function, is the code that's run when the function is called. And just like with if statements and else's and whiles and fors, we have a pair of curly braces. And inside those curly braces, you can put whatever code you'd like. That code within the curly braces is the body of the function. And you've already done this a whole bunch in setup, in draw. Every P5.js program that we've used so far, you've written functions, but we sort of glossed over it and made it sort of like part of the background infrastructure. Now, we're sort of like removing that boilerplate-ish perspective and making these things part of our kit, a tool that we can use. All right, so arguments are optional. You can have a zero argument function, just like we did in the lab, by having a parentheses that has nothing in it, no variable names. This means you can call it with nothing in it, which is kind of neat. Just like if you call random with no arguments, you will just get a number between 0 and 1. Now here's a look for a function, and this has something we didn't actually use in lab. So this function returns a value. Here we have average. We define the function, so the function keyword. The name of the function is average. It takes two arguments, a and b. Then we go to the body of the function. And what we're doing here is we're making a new variable with let, which means it only exists within inside these two curly braces, and will go away after the function is done. And when a function is called a second time, it will need to be recreated. So we have AVG, short for average, and we give it a little mathematical formula here, a plus b divided by 2. Right, so the average of two numbers. And then we have this return keyword, average. Now what return does is it takes one variable name, or a statement that reduces to one bit of data, to one variable, to one data type, and returns it. And that means it can be used elsewhere. It returns a value back to where it was called from. Let's take a look at this. Let's see, pass variable average. Whoops. So here we are. We have a function set up. It's fairly bare bones. Has a basic frame rate, great canvas, background. Now the first thing we have here, starting at line 7, is a function called average. So function keyword, JavaScript says, hey, we're going into declare function mode. We, like say, looks for as a name, which we give it, call it average. And we need to give a function. We need to tell it what its parameter list is. In this case, two variables, a and b. We end the parameter list with a right parenthesis, and we have a left curly brace, which says, hey, let's start the block of code that this function consists of, that will be ran when the function is called. Okay, so we have our let average be a plus b divided by 2, and then we return average. So this passes the value back to the calling code. So we have our draw function here. Let's see how this is used. Let num equal 100. Let result equal average num, comma 50. All right. So what this does here, when we're calling this average, when we give a variable name and we have parentheses after it, it's telling JavaScript, hey, treat this name as if it were a function. So look for a function called average that takes two parameters. Right? And so because we've already looked at this code because it happened before time, we know that that average is already a declared function, so we can use it. Okay, so now when average is called right here, we have these two parameters, num and 50. Those get passed. Num gets passed to a, so num has a value 100, and that value 100 is then assigned to a, which exists just within this function. And then we have 50, which is then assigned to b. So a is 100, b is 50. And we run our little math statement. A plus b divided by 2. So 100 plus 50 is 150, divided by 2 is 75. And that 75, since we return it, now average sort of gets replaced with that. Right? And then this 50 here is the thing that is then assigned to result. And then we print the result. The 75 is returned. And if you run this and you look at the list, you'll see this every frame is printing the value 75. All right. I went a little slow on this. just to get us all back into speed. And I wanted to introduce this idea of return to you. Do you have questions about this? Like solid understanding now? Okay, I got 3 thumbs. That's success. All right. So now that we're experts on functions and returning values, you can see that this is the argument, this is the function keyword, and then we printed 75 when it was called, like we just looked in the example. Now I want to give you a little guide here. This is a little to-do list, a little formula on how to make your own functions. So first, you can just write what you want and draw. Make something happen. This doesn't mean you have to like think ahead of time, like what should be in functions? Oh my gosh, how should I make this whole thing? No, you can do this a little bit experimentally. You can do this through trial and error, through practice, and through actually putting pen to paper, as it were. So you can put code into draw. Make your tree, make your sun, make your stars. Then test it and make sure it does what you think it should do. Then you can take that chunk of code and copy and paste it outside of draw. And then, whoops, I left a void in here. Oh my gosh. Function. Functigion. There we are. And it capitalizes, not. Oh, sorry, I'm fixing it. I'm going to be obsessive about this just for a moment. And then take that code that you just copied and put it inside of a quick, easy function. You can use like foo as like this traditional, like, oh, when you're giving a function example, use this name. Just like X is like you use it for default for like whatever number you're talking about, or A and B are good default names, or I is for iteration. Foo is our classic computer science for name, like for a variable name for just like an example. And bar and bas are the ones you use after that. So you want to make a little function. You can call it foo to start with, and then put your code in there that you just verified, that you saw worked in draw. And then replace that code in draw, comment it out, delete it since you already have it below, and then call your function. In this case, you can call foo and see if it still does what you thought it would do. And if you need it to be more flexible, like let's say you drew a star, and then you want to be able to change the size of the star, then you can add in the size as input to the function. You can make your function have some parameters that takes X size and Y size. And then you can change the code inside your function to use those variables instead of whatever probably hard-coded value like 300 and 200 you put in for X and Y. And then use those parameters. Draw your function in a few other ways. Make sure it works. Right, so this is a good slide to keep around. So you have access to all the slides and everything, but this is one that will come in handy time and time again, this little formula. Particularly when we're doing assignment 4 and when you're prepping for the midterm. Let's draw some stars. So I'm going to go to the draw star example. We're going to see that it draws a star. Very simple star. It uses 3 lines to draw a star. Okay. So first we have our setup, small frame rate, canvas size 400, 400, background of 255. And we have this code we have in our draw function. We have this bit of code here that draws the star, where mid X is 200, mid Y is 200. The main length is 400, and then the second length is main length divided by 2. Right, so we're drawing a star that is basically 400 and then, or 40 wide, and then has a slightly smaller length for the smaller lines. So you can see that here, where we have a line where we take, it basically gets, an X start, X1, Y1, and then X2, Y2. And then we draw another line, set the stroke weight to 1, make it a little less chunky, and draw some smaller lines. And you can see, without going into all the math here, you can see that we basically make, this consists of 4 lines. One that's entirely vertical, one that's entirely horizontal, and then 2 diagonal lines that are of slightly smaller stroke width and slightly smaller line width, or line length. So this main length is the sort of like the plus version of the star, and the second length and the lower stroke weight is for the X portion of the star. All right, well, that's great. We drew a star. So let's follow our formula. Now let's make a function, perhaps called draw star. Right, so we have our draw star function here. We want to take all that code we had above. We want to put it in here instead of watch me copy and paste a bunch of things. Can look at this code. The only change here, we'll go ahead and make it exactly even. We'll do all the steps. Put our code in here so it looks like this. And then this doesn't have any parameters at the beginning, right? And we'll take this code. We'll comment it out because we don't need it anymore. And we'll call our draw star function. And run it. Hey, we drew a star, but all that code's out of main, and all that code is in the function. Great, just like we did in the lab a bunch of times. Well, now let's think about the parameters. Well, we have these variables in here, mid x and mid y, which show us how, like where the middle point of the star is. Now let's make those 2 parameters instead. X location, y location. So now we want to take in an x and a y when we call our function, 2 variables, 2 numbers, and use those, interpret those as where we want the star's middle to be. And that's great, because now we can just take x lock and y lock and put them here, and use those with mid y and mid x. If you wanted to also refactor this, you could just replace mid x with x lock and xy all throughout here. But this is an easier, this is a great way to do it. So you preserve the original code if you're a little unsure. Then now it doesn't work. Why? Well, we were expecting a number of parameters and we gave it 0 parameters. Uh-oh, let's fix it. Instead of just calling draw star like this, let's put a star right in the middle at 200, 200. Yay, we got a star. Let's draw another star. So we have a canvas of 400 and 400. Where should we put the star? I have 300, 200 in here, but does anyone want to be a little interactive? Anyone want to pick some numbers? 100, 100. Just like the one right below it. Thank you. All right, now we have 2 stars. Great. Let's go ahead and add our 3rd star. Great, we've reused our code. We've made it parameterizable, so it's flexible. We've made it reusable, so we can call that code again and again and again. We're sort of unlimited in the number of stars we can draw. We're only limited by our computational power and our imagination. And it's fairly flexible. Like if we could make it more flexible and to replace the main length value by a size, and we can have it grow and shrink, and it's sort of like star diameter. We can make it, set a twinkle rate and make it twinkle, that sort of thing. So we now have functions with parameters. Now that didn't return anything, but it was more of a complex function. Now, I want you to look at this a little bit. There are two print statements in this function. I want you to look at the function, read it, I'll give you a moment, and I want you to tell me or understand what values are printed. And I'll just take the number values of test val, because we know that there will be before call test val 1 be printed, then after call test val, and test val also be printed. The important part here is what the test val value is at the time of print. And by the way, and I think Adam just discovered this, don't use print outside of setup or draw. Because if you do, it'll actually try to print the page. Like you'll get the print dialog that'll pop up on your screen, and that's not what you want in a large for loop or something. All right, who thinks they know what the first print statement is? The first value is? Where we're calling, where we just want to know what test val is. This one should be straightforward. Yep. 5, right? Because we didn't do anything to change it, right? We assigned it here, and then we just directly used it, right? Okay. Now, we call pass variable with that test val, which we know is just 5. We just printed it out, and we put it in here as parameter A. All right, what is test val here? After we run the function. I see wheels turning. I'll just give it a moment. Yeah?
Is it 10 because it's been moved on top of?
Let's take a look. Oops, come on. My mouse is acting up on this surface today. All right. So, as we can see here, first call is 5, second call is 5. What happened? What happens here? Does anyone think they can explain this? Yeah, go ahead.
Because pass variables are things in a predefined variable?
I mean, that is not completely unrelated, but it's not exactly what's going on here. And let's take a guess. All right, so what's going on here is that when you pass a variable in to a function, it passes a copy of it. It passes the value, not the variable itself. It doesn't pass the box. It makes a new box for it. So it's isolated from the outside code in an important way. So what's happening here is we do pass in the 5. So first of all, we set A to 2, test is 5, return in 5. Oh, did I set A to 5 in the slides? 1 second. Yeah, A is 5. We just do let A to 5, test val is 5. Okay. There we go. So test val is 5. We just declared it above. We pass in test val, which should be A plus 5. A comes in here. So this A is sort of ignored. Test val is 5. Or test val is 5, so 5 plus 5 is 10. A is 10, but there's no return, right? We're never capturing that value. It's not coming back to us in any way. We just did some empty computation, like threw it away into the void. And so we come back here and, test val was never changed. It was never sort of like on the left-hand side of an equal sign. so it never got updated. Like if we put test val like here, then, whoops, test val undefined. I misspelled it somehow. It's very hard to see my tiny screen. Pass variable takes test val gets that. I didn't actually change anything. Pass variable takes A. Anyway, you'd have to capture it, capture the return statement. I won't debug this live in front of you all. But so it didn't change, so we print 5 again. And then here, we also just print the value of A. Yeah?
Is it undefined? Should they return A?
Oh, because there's no return value in the function. Yeah, you're right. Thank you. My brain. Sometimes in front of class is a little harder to think adaptively. So if we did return A, thank you. Now it's 10. But that's not what we had. So therefore it's not returning anything. So test val gets undefined. It's not, no value is sent to it. So when we try to print it out, it says test val is undefined. So here, we also print A. So there's a mysterious value A hanging around to find a global scope. So JavaScript can get a little weird. This is why I want you to be very careful with your variable names and try not to overlap them if at all possible. Because what happens is inside of this function, it has this thing called A right here, but also it can use this thing called A here. And it has to have some way of disambiguating which one to use. So it always uses like the closer one to it. In this case, the one that's defined right here. Right, so there's a whole set of these. I'm going to ask you to remember this variable name convention. Just know that conflicting names are bad and try to avoid them if at all possible. All right, thanks for helping me debug that on the fly here. All right, so variables are passed by value. That's also called passed by copy. You'll see this around. And we're going to use them the way we're using them here. They'll mean the same thing for us. That means the function just gets the value of a variable. So if the variable is 100, it's the 100 that's passed and assigned, not sort of like the variable itself. So if you had this variable that had 100 in it in a box, like we talk about variables are boxes with labels pointing to a box, what happens is inside the function, you make a new box. And then you say, oh, what's inside the first box? Okay, the second box gets a copy of that, gets the value of it. And so now you have the second box you're working with inside of the function. So when you make changes to the variable, it won't make changes to the outside variable that you passed in for it. They're isolated. So the output of the previous program was 5, right? So we pass in test val here. Test val gets used. Test val, the 5 gets copied into A. A is 5, so 5 plus 5 gets passed back to A, so A is now 10. Now this box we created just for this function, this A, is now just like at the end of the function thrown away. The box is removed. The box is sent back for the memory to be used again by someone else. And so the test val here is its value had never changed because its box was never assigned to. All right. Kind of looks like this a little bit. So we have test val coming in at 5. A initially gets the value of 5. Then it gets assigned the value of 10. That 10 is never returned, so test val remains 5. Now there is a thing about pass by reference which will be meaningful for us starting next lab and next class when we talk about objects and arrays. We've already used some of these. If you've used a color object, then you've encountered this before. But so far we've been programming without objects, which has made our code a little funky and a little less usable and a little more verbose. So we're gonna learn that next. That's sort of like the last piece of the puzzle we're going to unlock, our objects and arrays. more interesting ways to store our data than just flat variables. Now, when you use objects or arrays, they're actually passed by reference. So that means the changes that you make inside the function will affect the ones outside of the function. But for our what we call primitive variables, our primitive types, our values that are sort of like built in to Java, they don't work that way. They work by pass by value. In some languages, as an aside, like C++ or C, you can use operators to determine whether you want to pass by value or pass by reference. These are the dreaded pointers and dereferencing operators that you may have heard about, where you use a bunch of ampersands and stars and try to figure out which memory goes to which areas, and using pointer arithmetic to move through memory spaces. So that's a little more complex. Not expecting you to learn any of that for this class, but that's sort of like where this goes if you follow this down to a more complicated level, to the next level of detail. So we'll come back to this when we know what objects are. But the reference here is that test object, the variable a inside of our pass by reference function would actually just get the value, or would point directly to the box of 5. So any changes you make to a would directly affect the value of test object, which is 5 in this case. Okay. Let's see which one of these examples we want to look at. We looked at pass by values, good object. We did draw star. We could look at draw stars. We could use functions many times and draw as many stars as we'd like. So what we have here is we started with the original code. So the original code is in here, with the void, star, and all of this. Or sorry, with that void. I forgot to change this from function star, which is commented out, so it doesn't really matter. So here is the star we use, the parameter of our function, right? The same star we looked at before. Has x, has mid x, mid y. I just drawn it here. So we did do the transformation instead of input x, input y. This is the fixed up version where we're using, instead of just like taking these values and just immediately assigning them to another variable here, we are going in and just using them directly. We don't need 2 boxes when one would do just fine. And we draw our 4 lines. Inside of draw, we had all this code before where we drew the main axis, another axis. We called the function, we called it with parameters, but now we can just call it inside of a for loop. Or, I'm sorry, inside of draw, and every time that draw happens, every frame, we're going to draw another star, count up, draw by 1. So we'll end up with 25 stars, so star 0 through star 24. And we'll be counting up. Right, and that's how they appear over time. If you added in a for loop in that one in the setup function, they would all draw simultaneously and you wouldn't see them sort of twinkle in. So that's sort of the effect we're going for. And we can set the frame rate to lower, like 3. Now they'll come in. And we could change the number that we draw by changing that number in the conditional inside of our while, inside of our if statement here. So we can draw 50 stars. And our star field will get much more crowded. And each one of these are drawn at a random x and random y within the range of 0 to 400. And this is a canvas 400 by 400, wide and tall. Right, we'll get enough stars on here that it'll look a little cluttered. Some sort of like weird Cylon star invasion. Do you have any questions about this code? We went over it fairly quickly. But I'm hoping you have enough scaffolding at this point to sort of understand the basics of what's going on here. Like, we didn't go through the math. Basically, the only thing we didn't do is go through the math of drawing the lines. which I'm happy to do during office hours or during lab if someone is curious. What do you think about the stars? Do you think you could make your own, like, whatever drawing thing you wanted to do and use it in a way like this? Yeah. Of course, people who have done programming already give me a thumbs up. All right. So this is the type of thing that you should, like, it should be a little difficult for you to do now, but it should be something within your skill set. This should not be an unachievable thing for you. Drawing stars. Happy little stars. All right, so we have that. Let's take a look at the sprout. So I'm going to give you a little preview of objects. So here we have a little sprout that animates and grows into a flower over time. One more time because I think it's fun. A seed, sprout, budding flower. Now, we do this with our time-based animation with frames like we've done before several times. We're handling the growth in sort of like stages of growth. Stage 0, 1, 2, 3, and 4. And the code for this, something you haven't seen before. So seed gets a new seed, but S is capitalized. Right? That's a little interesting. What's going on here? We haven't used this new keyword before. It's new to us. And all that we're doing here is calling seed.draw. What's this dot thing? Do we just smush a variable name together with a function? So this is sort of a new capability for us. So at the bottom here, what we're making, just like we defined functions to reuse them over and over again, this is defining what we call a class or an object, which is a bundle of functions in a bundle of data all together in one little encapsulated bit. In this case, a seed. And what does a seed have? Well, it has a location, X and Y, and it has when you started planting it, when it was planted. So that way it knows how to grow itself. It knows what stage of growth it should be in over time. And then it has its own draw function. So when we make a new seed, we can call seed.draw. And what that does is it looks in that seed variable and say, hey, are you an object? If so, do you have a function called draw associated with you, inside of you, defined in you? That's what the dot does. We'll go over this more extensively in next class. Right now, just a little preview. And so our draw function, we simply turn off stroke. See if it's the first sprout. Then we see which stage of drawing we're in. So we look to see when we were planted, and then we compare it to the current time divided by 1 second. So every second it grows into a new stage of growth. And then we simply look here with a big if statement. If we're between 0 and 100 milliseconds, so we're in stage 0 of growth, we draw seed. But if we're between 100 milliseconds or 1,000, 2,000 milliseconds, we're in stage 1, which we draw our first sprout. Between 1 second and 2 seconds, or when 2 seconds have elapsed, we go into draw stage first leaf. When 3 has elapsed, we go into big sprout. And when we're past that 4th stage, go into 5th, which is draw flower. And then we stay at draw flower. And so you can see each one of these little draw functions just simply is the little graphics for that stage. So a little ellipse for the seed, it's brown. Then we do, for first sprout, we draw seed. So we draw the brown thing before it, and then we put a little green sprout. And then with our first leaf, we draw the seed, and then we add a little more sproutness to it. Then for big sprout, we draw the seed and add a bunch more stuff to it. Then finally with draw flower, we draw the big sprout in front of it, and we add a big old flower on top. Right? And that's the code. We just encapsulate a bunch of different draw commands and use them in a patterned way and put them all in a class called seed. So now if like in your code, like you could use a bunch of seeds and like this is the real like heart of your code, right? This defines what a seed does. Just like function says, hey, we have a function named this thing. Now we have a seed that has these capabilities and this data in it. The constructor is the thing that when you call new seed, it handles these values coming in and assigns them locally. And then we just call seed.draw and it handles itself. So a little bit of self-contained functionality, which brings us to this. 4 and 5. Right, so that was a little bit of preview. I don't expect you to understand all this. We'll go over it more in lab. But this one I wanted you to see a little more times because this is a slightly more complex. And we're going to introduce these and arrays together. So both take a little bit of lift. But at this point, you're all like experts. You've been giving me really good questions in office hours, and you're really good in labs. So I think you're kind of ready for this. All right, any questions about functions? Cool. Let's talk about assignment 3. We got 25 minutes left. We can do assignment 3. All right, so as always, you can find assignment 3 here. This just happens to be in collection 14. So roughly like a little over half the class had said they'd started. I'm hoping almost all of you have read this by now. So what we're doing is we're starting with something that looks like this. Oops, let me, small screen size. Where we shoot a little space exploration vehicle at a planet and either land there or we don't. Well, we missed. Start over again. All right, so we have some code for starting over in here. Your goal is to end up with something that looks more like this. Where there's a couple obstacles in the way, and you can stop the obstacles, and you can restart when you're stopped. So if you hit the planet, we want to restart again. So you have access to this video. I'm playing it through VLC because of browser stuff. But this is, linked right there in the README, in the tutorial text portion to the left on your sketch. Now the important part here is that this assignment has a few pieces to it. Let's take a look at them. So the first is to modify the planet. Now what I want you to do here, and is this big enough for folks in the back? Should I make it a little bigger? Fine. So I want you to customize the planet in some way. That's your stage 1. So all these portions are worth 25% of the project grade, or the assignment grade. The first one's easy. You may notice that we do have a progressive grading system in this class where the first steps are easier and they give you proportionally more points for their difficulty than the later stages. It's classic assignment design. Pardon me, classic assignment design. And I want you to customize your experience. So basically, I want you to change the planet in some way. Color, size, speed. And if you change something like size, you want to update the collision logic, which we'll look at to make sure that the actual size of the planet matches the collision with the spacecraft. Now, personally, I'd like to see some rings, like Saturn style rings would be kind of fun. Maybe have it have an orbiting moon. So this is a chance to have a little bit of fun. And you could have the orbiting moon be one of your collision objects. We can, which was part of this as well. All right. So modifying the planet, pretty straightforward. You've done stuff like this a bunch before. Second part is add a restart mechanism. So notice when I play and I hit the planet and I succeed, I can't click again and restart. So I want you to add that. So if it's stopped, so if the game is sort of like, if you've been launched and you've been stopped in some way, whether it's success or whether you've flown off the edge of the screen or whether you hit an obstacle, I want you to be able to click again in that state and bring the ship back to the platform. Notice there's a has landed variable in the code. That's something that'll be very useful for you for this task. We've already done part of this for you. So there's a bit of code here, but like the solution for this entire lab is like maybe 15 lines of code. Not that much. You've already made projects bigger. But it's the correct 15 lines of code that we want. All right, start 3 is implement gravity. So this one, I want you to slow down the ship as it launches. So I want you to incrementally pull back. I guess it isn't full gravity. If you do full gravity, that'd be awesome, where it actually gets faster as you get closer to the exoplanet, the other planet. For this case, I define like this gravity interaction as your ship just getting slower as it moves. So every frame that the ship is moving, or every increment of time, I just simply want you to reduce the ship's speed by a little bit. And since the ship is actually traveling in negative y because it's going up, it's actually adding to the speed, makes it go less up, less upness. So this is sort of like simulating gravity pulling your ship back down to the planet. Like I said, if you want to do it so that the gravity pull of the planet makes you go faster as you get towards it, that'd be cool too. I would be happy to see both of those, or either of those. And then stage 4, this is adding floating obstacles. So I want you to add 2 obstacles that somehow move around the space that can interfere with your ship getting to the planet. Not only do we have the planet moving, we also want a couple objects to move around and be obstacles. Now, that sounds a little frightening, but we have a lot of the code in there for you. The planet itself is already kind of an obstacle. Just the result from when you hit it is different, right? You print out great success when you hit the planet, but when you hit another obstacle, we simply want you to print, like game over, failure at a launch, whatever fun quippy thing you want to put in red text in the middle of the screen. And here's a little guide to implementing some of this. So you're going to want to make some new variables. You're going to want to draw an obstacle. And you want to see if the ship's position overlaps the obstacle's position. We'll talk about how we do that with circles, because circles are actually really easy to do this with. And then if the collision happens, you can display mission failed. I will take other fun, pithy things. Be creative. So we use a distance function to make this calculation. All right, so these are the basic items. Let's actually go through the code now so you can get a better understanding of how the tasks for this exercise would actually be fulfilled. So first, we have our variables that control our planet. So we have our planet's x and y location. Then we have our planet's size, or its radius. And then we have its direction. So this is the direction the planet's currently moving, but you notice the planet moves back and forth. So when the planet gets to a certain spot, we actually flip the direction, times it by -1. So then it goes in the other direction. And then when it hits the other edge of its range, multiply it by -1 again, so it moves back this direction. I guess that would be opposite for you. Starting with this direction, yeah, anyway, whatever, it's fine. You can figure it out. And then we have our variables for our ship. We have the ship's x, the ship's y. So its position, we have its speed, we have its size, its radius, and we have whether the ship has landed or not. We have a variable that we want to make sure, like, we want to keep the current state. Should this ship be actively going now, or has it hit something and has been stopped? All right, so our setup function is actually pretty easy. Just a simple canvas creation, 400 by 800. And we make a background, which is a bluish midnight escape. Maybe we should use our star function and put a bunch of stars in the background. So first what we do is we manage our planet's speed, right? So this is our managing the planet's location. So right now the planet's just moving along the x-axis, right? It has no y movement, and that's fine for you to keep. So what we're doing here is we're simply adding to the planet's x, the planet's speed times its direction. So if it's moving left, it'll be a positive speed times a -1. So it means it's moving left. So it'll be going less x, moving in the negative x direction. And if it it's going to the right, this will be 1. Planet direction will be 1. So planet speed, which is a positive number, times 1 will be moving it in the right direction, the direction to the right. And then we have our borders here. So if the planet is less than 350, planet X is less than or equal to 350, or the planet is less than or equal to, or greater than or equal to 350, or less than or equal to 50. So it has a 50 margin on either side, since it's a 400 space. Then we reverse the direction of the planet, which simply, we say planet direction times equals -1. All right, and then we draw the gray launch pad that the ship starts on. Then we want to draw the planet at its current position. We've figured out what its X and Y locations are, so we're going to draw it. Then we do a quick check. We want to manage this where the ship is. So if the ship has launched or not, we want to give it manage its speed value, or we want to manage its location. So if the ship hasn't landed, the ship's in motion. So we want to increase ship's Y. And ship speed in this case is negative because it's going up. So you actually be making the ship's Y value, making it lower, going towards 0 every time through the loop. And now here's our check to see if the ship has gone off the end of the screen. So if ship's Y value is less than 0, meaning it's past the planet, it's past the top of our canvas, we return it back to the platform. So the platform location being 200, 730. We set speed back to 0 and has landed as false. So now it's just sitting at 0, not launched, back on the canvas. Round 2. That first ship's gone to oblivion. We just make a whole new one, or it teleports back. I don't know, whatever the metaphor is here. Either way, you now have a ship back at the landing pad. All right, and so then we draw the ship. The ship is a little cyan circle. That is at ship X, ship Y location, and its ship size. Then here is an interesting function. Let's see if we can. I guess it would be hard to see it. We'll scroll over. So basically what we're trying to do here is see if the circles overlap. Does the ship circle overlap with the planet circle at all? That's how we do collision detection, right? Does anyone know that sort of like the fast way to do this? Can anyone like interpret this distance function here, this call for me? So distance simply returns the distance between 2 points. So the ship's X and the ship's Y, and the planet's X and the planet's Y. So it takes the difference between the 2 locations. And then says, is that less than the ship size plus the planet size divided by 2? What are we doing here? So when we give a size to a circle or an ellipse, what does that size mean? We say it's the size of the circle, but what do we call that in math? Yeah, it's the diameter of the circle, right? So we have the 2 diameters of the circle. We have the distance between them. So if you want to see if they collide, how can you use that information? I put it to you, UC scholars of renown. Well, first off, the diameter doesn't help us too much. We actually want to use the radiuses, right? The radii. Radiuses? Radii? I'm not sure exactly what the exact term is for the plural. So if you have their radiuses and you have the distance, you can tell if they are overlapping or not by just seeing, okay, is the distance between them greater than the sum of their radiuses? If it's greater than the sum of the radiuses, there's some space between the circles. If it's less than that, they're overlapping in some way, right? So it's actually a fairly little intuitive way to see if two things are occupying the same space, given that they have some volume, some size. Do the edges of the circles overlap? The distance, is the distance less than, the 2 points, less than the two circles, less than the sum of their radiuses? So you can use that formula, that basic thing for this, seeing if the ship has collided with the planet, or seeing if your obstacles that are floating around have also collided with the ship. I guess you can have a hard mode where if one of the obstacles collides with the planet, meteor strike, game over, you wouldn't want to live there anyway. Destroys this space platform. We don't have to go that far. I'm just wanting to see if you have a ship that collides with an obstacle. So the obstacles, if it's a circle, it's position, the distance between the position and the ship. You want to compare those two, and if it's greater than the radius of the obstacle plus the radius of the ship, then they're not collided. If it's less than or equal to, they're sort of like touching if it's equal to, maybe that's a gray area. And then colliding is when their distance is less than the sum of the radii. And in games, we call this collision detection. This is sort of like the 101, like the simplest version of collision detection. This is why when you open sprites in sort of like game editors and things, there's usually like a little circle around them. That circle is for when you want it to touch a power-up, when you want it to touch spikes, when you want it to see if it's standing on a platform or not on the ground. We want to know what it's colliding with and what it's touching. And circles are super cheap to do this with. And this is actually the expensive version of it as well, because here we're calculating 2 square roots. We're actually calculating a square root with distance. You can actually just, because of the proportional, you can use the squared versions of the distance value and not normalize it by by taking the square root. Something for another day, but something to ponder if you're a math person or want to explore how to do this fast and efficiently. All right. So here, if there is a collision with a ship and the planet, we want to set the fill color to white. We'll set text size to 20 and print great success at 140,400. And we set the ship speed to 0, which effectively stops it, and has landed is true. Right? Does that make sense? Like those outcomes if one has touched another? Print the text, stop the ship, has landed. All right. This brings us to our last little bit here, the mouse clicked. So you're going to want to modify this function quite a bit. This will be part of your portion 2, add a restart mechanism. Here, instead of just simply, hey, we're giving the ship an initial speed value, what we'd like to do here is say, put a little bit of logic around it. Say, hey, if has landed, pull the ship back to the platform and start over again. Anybody else want to put a guard around it to make sure that you can't just click and keep resetting the ship's speed whenever you want, particularly with gravity. So you're going to want to see if the ship speed is at 0, so it's on the platform ready to go. Then you can set its speed to -10. Otherwise, you probably don't want to modify its speed. So there's a few things here that I'm looking for. All right, so we went over every single line of code in the base version of this project. Are there any questions? Perfect knowledge transference. Wow. Got up here and rolled a 20. I know this is going to be a lot for some of you. I don't want to downplay this. This is why I'm going to have 2 separate office hours. I'm going to send out a schedule tonight. I'll have an office hours on Tuesday and office hours on Wednesday. And feel free to come in and ask questions during labs. I want to give you as much help as you want, but I want you to understand this stuff. If you can do well on this, then you're probably going to do pretty well in the midterm. So the goal, the pedagogical goal behind this assignment is to bring together things that we've done so far. Interaction, conditionals, and variables into one cohesive unit that has some depth to it. At the end of this, you got a simple game, right? Put it on the App Store, make $1 million. All right. Pausing a moment for questions, see if anyone has any. If I ever riffed enough. We got 5 minutes left. Any questions about the midterm? Or the schedule? Or functions? I want to make sure you're getting value for your time. We ended just a little bit early today. Not too much early. Yes?
Midterm is going to be pencil and paper. Is it going to be like short answer responses to questions generally?
Yeah. So it'll be a mix of multiple choice, fill in the blank, like match the things. There will be a little bit of like interpret this code and tell me what the output is. And there'll be like a little bit of like, look at this grid. What does translation and rotate and things like that do? Right. So it'll be all things you can easily achieve with pencil and paper. The most comprehensive thing will probably be like, okay, describe this concept in 2 sentences. So it's not going to be any big long essay questions. You won't need a blue book. You'll have plenty of space to work. We'll have scratch paper for you. I will send out a policy on what you can bring to the exam. It's likely I'll just like say, hey, have fun with your standard index card size set of notes. Draw as tiny as you want. No magnifying glasses. And we'll take it from there. All right. Everyone, take care. I'll see you all tomorrow and Wednesday in the lab. And I'll post office hours and see you then. And on class on Wednesday. Take care.